Thank you, Chairman. Hello, everyone. Thank you for joining my presentation. The title of my presentation is multiple two-mass stamper for vibration control high-rise buildings. This is a new device compared with a conventional two-mass stamper. It's a course with my students, and I come from Taiwan. A two-mass stamper is simply a dynamic system with mass, stiffness, and damping elements connected to a control structure which has a vibration problem to transfer the system energy of the structure to the mass damper and dissipate it by the damping element through tuning both frequencies. Here is a demonstration of the vibration control by the two-mass damper. You can see significant reduction of the vibration or the structure vibration by the two-mass damper. It's also observed that the movement of the mass damper is much larger than the structural displacement. So that it needs space for the mass damper to move. That's the practical consideration. So today, the outline of my presentation just to show you the fundamentals and the state of practice of the conventional two-mass damper, and the control philosophy and optimal design of the new type multiple two-mass damper which we proposed. And we try to use the new type of mass damper to a real structure, which is a high-rise building, and doing some experimental tests. So we made a scaled-down model structure, and of course we have to do the component test of the system, and do the combined system, shaking table test or the combined system, and I give some conclusions. Here I show you the real implementation of the conventional two-mass damper in our slender observation tower and long-span bridge and a pedestrian bridge and high-rise building to reduce the vibration due to natural excitation like a strong wind or earthquake or human activity. Here's some examples in building, tower, and bridges, such as the high-rise building in Taipei, which is longer than 500 meters. You can see all the structures are very slender and with long period. Like, for example, the first building used two-mass damper to reduce vibration is the John Hancock building in Boston in 1977. The natural period is around 7 seconds. So the building is subjected to vibration, have significant vibration due to the strong wind. And also some new recent installation, like the Skytree in Tokyo, and Canton Tower in China, and Millennium Bridge in the UK, etc. Here is the photo of the two-mass damper here in Taipei 101. So far, it's the largest mass damper in the world. It weighs 606 tons, made of steel with diameter 5.5 meters. The allowed movement of the mass is about 5 meters. It costs $4 million US. There's some controversies about the mass damper for the seismic effectiveness in 1980. So we do a very intensive study. So we give a conclusion in 2001 in the Journal of Sound and Vibration. It concludes that the two-mass damper is effective as the excitation frequency are located within the operating frequency range. So for our structure, there's an operating frequency for the two-mass damper. So if the excitation is located, the frequency of the excitation is located within the frequency range, operating range, the two-mass damper will be effective. And also we know for our general structure, there's a multiple degree of freedom system. So that's we have to decide which mode we have to control. So usually we control the dominant frequencies. So we can write down the equation motion of control the mode property, we need to know the control property like the frequency, the damping ratio, and the mode shape, so that we can decide the location of the mass damper. We can write down the equation and define a performance index, which is a model response with and without the mass damper, to minimize the performance index to obtain the optimal parameter of two mass damper. Here's the result. Show us that even the earthquake excitation from the hot side, this is a soft side in Mexico City, and the hot side from Japan, we can see the significant reduction of seismic response was achieved in the dominant frequency of the control structure and the earthquake excitation. This is a research for the conventional structures or the conventional two-mass dampers. However, there's two practical considerations. One is called frequency tune effect. We can either found that the control performance of the two-mass degrades very, very fast as the two-mass damper does not tune its design the frequency. It may cause by the modular error, structure identification error, system variation, or the fabrication error. That means if the structure system varies, the mass damper has to be adjusted to retune to its desired frequencies. Of course, can be solved by accurate system model or model updating, reliable system identification techniques. But we propose use multiple two-mass damper with wide frequency bandwidth. This is the basic concept for a single large mass. It works like a rifle. However, if the frequency or if the structure system varies, the control effectiveness of the two-mass will degrade. So that's if we divide the big mass into several pieces, and we control a band of frequency, they will be more robust. Also, another advantage of the multiple two-mass damper is to control multiple modes with the same mass. So here is another consideration is the large stroke I just mentioned. We need the mass need a larger space for two moments. For example, for the mass ratio of the mass damper to the main structure, about 1%, the moment of the mass damper is 3 to 5 times of the structure system. So that we develop a two-stage optimal design procedure to consider the control performance and the stroke together to define a new performance index, to minimal index, and to introduce a weighting factor alpha. So let's say if alpha equals 0 means the conventional design, alpha equals 1 means we consider stroke in the design process. Here I show you the design procedure. And also in the design procedure, we define and we determine the elements, the stimulant elements and the damping coefficient all the same for all units of the two-mass damper. And here is the equation to calculate the parameters for the stimulus and for the damping coefficient and for stimulant coefficient, which is a change in the mass of each mass damper. That's quite easy for construction. Here I show you the example. If alpha equals 1/4, that means it's not so. To consider both the performance of the two-mass damper and the stroke together. It will just sacrifice 6% of the control effectiveness, but gain 60% reduction of the stroke. So it shows the merit of our two-stage design procedure. So all the results are shown in one book chapter, one chapter in this book. And both the invention patent were granted in Taiwan and the United States in 2004 and 2008. So we try to implement our proposed new type of two-mass damper to a high-rise building. Here is the Tokyo building, which is a 38-story, and we'll try to control the weak direction, which means the y direction. And the fundamental period is 3.5 seconds. The damping period is quite low, just 1%. Usually, the design code requires the building to have a 4% damping ratio for the dominant mode. The total weight of the building is 34.6 thousand tons. To consider the capacity of the earthquake simulator, we made a scaled down model structure which is about 6 tons. And the frequency, I mean, the frequency or the period, the exact same at the target building, and the damping ratio is 1.6%. We made our 3 units of friction type two-mass damper, and with a stop and a lock device for fill and staff at both ends of each unit. Here show you the total weight, the weight of each unit, and the allowable short is 50 centimeters. And we have to do the component test for each unit. Here show you the photo. Put the 3 units of two-mass damper on the earthquake simulator. By doing the sine sweep, we can find the frequency of or the period of each unit to match the frequency we desired. And also develop an analytical solution, analytical model, try to predict the behavior of the mass damper of each unit. You can see the response of each unit and the energy dissipation, quite agreement, very good agreement with the test result. And we're also doing the second depth test for the combined system. Here show the photo of the main structure with 3 units of the two-mass damper. Here, the test result. The photo show you. The left side is a structure without mass damper. The right side is structure with a mass damper. And they show we are subjected to our real earthquake excitation. We can see the structure with a two-mass damper cease quite earlier than the structure without two-mass damper. And show you the mass damper is quite effective in reducing structural response. We also, of course, to record the time history of the structural response and the response of the two-mass damper, we can see the structural response are reduced by 40%. And the vibration duration of much shortened by the mass damper. For example, the light line is show you the structure without mass damper is less than 30 seconds. With much damper is just 18 seconds. So significant duration was shortened to assure the comfort of the human. And all the two-mass damper units are moving within the 50 centimeters. We also develop an analytical model to predict the behavior, dynamic behavior of the structure, and also for each unit of the two-mass damper. 2 analytical models were developed. One is a friction model. Another one is viscous linear model. So here we can show you it's quite useful and very accurate. The predicted structural response agree very well with the experimental response for both the structure and each unit of mass damper. And we also develop a viscous model that's for practical use, because usually the practical engineer use viscous damping ratio to indicate the control performance of vibration control devices. So here I show you the result of the predict response and the experimental result, and experimental result, and also show us that our model structure with proposed tumor center can can get the abdominal model damping ratio up to 8.3%, from 1.6% to 8.3%. So let's show you the control performance of the tumor damper. We also tested the stop and lock devices. We use a shock absorber or rubber buffer to stop and lock of the mass damper if it exceeds its limit. And then we use the hook and rod to lock the mass damper. Here show you the test result. Yeah, you can see one of the mass damper locked during the excitation. So you can see the tumor number 3 is locked after 9 seconds of excitation, but the 1 and 2 are still operating, and also effective in vibration control. Here the whole systems. We transfer all the technology to the Chang Lin Steel Structural Corporation to integrate and construct the whole systems. And here show you the company in Taiwan to make all the components like a spring, damper, the guide rail, and the mechanical fabrications. So here gives some conclusions. From the analytical and experimental results, shows that the multiple tumor damper is effective and reliable control devices, and less interference than other energy dissipation devices, especially for existing structures. And it shows it's more robust than a conventional tumor damper. And the very good control performance of the proposed multiple tumor damper have been confirmed through the analytical and experimental verifications. And also the mathematical model we developed can predict the dynamic behavior for both the structure and the multiple tumor damper quite well. And the stop and the lock devices work well. Even one unit of the tumor damper is locked, the other can still work to reduce the vibration of the structure. Thank you for your attention.